Know about Ravi here. Maybe I should have prepared some slides to talk about Ravi first. But maybe what I thought I'll do is, since we don't have internet connection, it's a bit hard to talk about it without preparing. So if you have any questions, we can come back to it later on. So this talk is about, it's a bit not from a user standpoint, it's a bit from a language developer standpoint. So, I don't know how many of you have tried to customize Lua as a language. Probably nobody. Oh yeah, okay, there are some people. So it's about that, So Ravi is a custom version of Lua, which I started back in 2015. And just I can't show you the proper formatted page, but what I can show you is the raw source of the documentation. But what is interesting here is what Ravi allows you to do. It has optional static typing. It's a pretty limited form of typing, like you can't express all kinds of types in it. It's got a defer statement which is built on the 5.4 to close functionality. It's got the generational garbage collector from 5.4. So essentially Ravi is based on 5.3, but some features have been backported from 5.4. It's also got the random number generator from 5.4. So you can, very quick introduction to Ravi, you can you can annotate local variables and function parameters with types. And there are only a few types supported. You can have integer, number, array of integers, array of numbers. You can say something is a table, that's a Lua table. You can say something is a string or a closure, or you can have something user-defined type. User-defined type is simply the name with which you register in the meta table, right? So in Lua, you have this concept, you can register your type name in the meta table using meta tables, right? So Ravi allows you to annotate a variable saying that this variable matches this meta table entry. So you can then, you can then write code like this. For example, here local T2 is a number array, or if this is a table or this is a number, you can write code like that, right? And the reason for doing all this is performance, obviously, because if we know the types, we can produce optimum code. And so essentially, what Roberto was describing for Pauline is kind of very similar to what Ravi is doing. It uses the I have a modified VM of Lua with extended bytecodes. And the idea is that with these extensions, you can generate optimum code. And when I was initially writing Ravi, my interest was in numeric computing, so my focus was really on numeric stuff. So I didn't care about the rest of it, which is why the focus was, so when you have a numeric array, it's not like a Lua table, it's an extended form of Lua table where there are it's a plain C array, right? So performance is much better. And so anyway, so there are lots of API functions and stuff you can do, and I suppose the interesting part is how you handle user-defined types. So as you know, with user-defined types in Lua, you register a name, you register a meta table, and once you've registered that, you can use that in the syntax like this. So you can say here, so here my type was a name registered in the Lua meta table. Registry, and so now you can use that as a type. And what happens is when this function enters, there's an assertion that this matches the meta table you've described. So if it doesn't, you'll get an error back, right? But there's no performance improvement with this. It's just useful for people who want to supplement their code with type information. So all of this is like the stuff that, and you need to sometimes you need to cast things, etc., etc. There's also support for a slice. You can slice an array, but these are Ravi arrays, so you can create a slice of it and work on the slice. That's a very, very short and quick introduction to Ravi. I'm not going to go into the details of this. But if you have questions, feel free to ask. Because I can't go to the internet, I just want to show you some documentation. So I'm showing you the raw documentation. I think the interesting part here again is what are the features in it, which I talked about already. You have optional static typing. You have type-specific bytecodes added to the VM. It's essentially compatible with 5.3. So most 5.3 code you can just execute. There are some limitations which are mentioned in the website. You have the generational GC from 5.4. You have defer statement. If people are familiar with Go, you know what the defer statement is. It's something that executes when the stack unwinds. You have a compact. I have a compact JIT backend, which is based on a product called Mir. There's a distribution with batteries called Suravi. There is a Visual Studio Code debugger extension to debug in interpreted mode. And the topic of today's conversation or today's talk is the new compiler framework that I've been working on. So that's what I'm going to actually talk about. This is just a very quick intro to Ravi, and also in terms of the history. I started in 2015. Initially, I had an LLVM-based JIT backend. Then I had a libgcc-based additional JIT backend. Then I also tried something called Eclipse OMR. So I've tried a variety of different JIT backends. Eventually, I've discarded all of them, and now we have only the Mir backend. The reason for discarding all of them is they are huge. Lua is small. So in the spirit of Lua, Ravi needs to be small as well. Otherwise, it's not really in the spirit of Lua. If it takes more than 10 seconds to build Ravi, I think it's not acceptable. So, with the new backend, it's very, very, very quick. You can build Ravi in 5 seconds. It doesn't make any difference. Okay, so now back to the presentation. So I'll talk about this new compiler I've been working on and what the benefits are. So essentially, we can have, when the code is executing in Lua, Lua has its own stack, which is in dynamic memory, right? And everything you are working with is on this Lua stack, right? So you can think of Lua as Lua functions just manipulating what's on the stack. Obviously, from a performance standpoint, when you have JIT compile the code, it's not so efficient because you're accessing memory back and forth all the time. There are situations where you could avoid accessing the Lua stack if you knew that some Lua variables are primitive types, they never escape to other Lua functions. Then you could optimize them and say, look, I don't need to put them in the Lua stack. So the new compiler framework does that. You can also JIT compile or ahead of time compile to shared library. And so essentially you get two languages in one also, because I've also have a new feature where you can embed C code inside Lua code. So that's what I'm going to talk about. So the previous approach, which is still there, so this has not gone away, The previous approach was that you have the standard Lua parser, which I have modified, which generates bytecodes. Again, the bytecodes are modified in the sense we have an extended bytecode set, which is then translated to C, and then we generate machine code using the JIT compiler. The new approach is like this. So, in the new approach, instead of generating Lua bytecodes, we have a new parser which generates an AST, abstract syntax tree. We then translate that to linear intermediate representation, which is again a completely new format, and then we translate to C. So, we don't have Lua bytecodes in this pipeline. And at the end, you can either compile it to a shared library, or you can JIT compile it. So, both options are available. And this compiler project is independent of Ravi, in the sense it's a standalone project. So, anyone can use it, but the final C code that's generated, it's like Pauline, it needs to know the internals of the VM, because it directly works with the VM data structures. So, therefore, it needs to know. Therefore, it's tied to Ravi as Ravi's VM, which is custom designed for this. So, very simple example. This is an old version of the code. So, this is, when I say old version, that is the previous JIT version in Ravi. So, here you have a function which takes an integer a, and it has a local b as well, which is an integer, and you add them, you add a, you multiply 10, you return it back. This is what would have been generated in the previous version, or when I say previous version, is the original JIT backend. So, what you can see is, because the type information is available, there are no tag checkings. However, these are accesses to the Lua stack. So, these are stack positions, and anybody familiar with how Lua VM is coded would recognize this. Basically, we get the stack positions, and then we set the integer value from the two variables, but every time we are accessing the Lua stack. And the Lua stack is a dynamic structure, right? It's not the C stack. So, this is the very simple example, and the same in the new compiler generates different code. So, here you can see that we still access for the incoming variable, we are still accessing the Lua stack obviously, but B has disappeared. B is now stored into a local C stack variable, and again what we return is the value from the C stack variable, right. So, the rest of the code is not shown here, but this is basically, and this is the new, I won't call it bytecode, new intermediate code. What this is saying is like add integer to integer. The first parameter is local a, stored at location 0. Second is also local a. The destination is temporary int, stored at location 1. And here we are saying move integer from location temporary integer 1 to temporary integer 0. Here we are saying multiply temporary integer 0. So, this t int is really on the C stack. These are not on the Lua stack. And this is possible because we are not using, we are not using the bytecode from Lua at all. This is generated new, this is newly generated intermediate code. So, this was just a quick show of what the changes look like. So, what are the goals of this compiler project is that, can we have a standalone lexer, parser, and also a compiler framework for Lua? So, the idea is that it's independent of the main language implementation. You can use it any way you like. Eventually, I'd like to have something which is totally standalone and reusable. So, if you wanted to just have a lexer for Lua, you could just use it. If you wanted to have a parser that produces AST, you could use it. If you also wanted to get an intermediate representation, again, you could use it. But of course, the code generation part is custom because you have to target a VM. But you could basically reuse the first two parts, without being tied to a specific VM. This next thing, the last point here is generated C functions. They just look like Lua functions. So if you say type, they will say function in Lua, but there are no bytecodes. The bytecodes are absent. So you can't debug them, for example, in Lua. So hopefully the idea is you can reuse the lexer and the parser. And here's an example of the AST dump. What I've been playing around with is dump it in a DSL format, which is directly readable from Lua. So you can see that this is a DSL which you can directly implement in Lua. Basically, functions, you create a function called expr function, which takes a table as a parameter, right? And you can basically directly read the AST into Lua from the output of this compiler. So if somebody wants to work with, this is not AST this is not the AST that you get with other parsers that you have available, because this has things like up values and everything has been resolved. It's not like the syntax alone, right? So it's somebody, if you want to implement your own Lua, compiler, you can start from here and do the rest yourself. So the linear IR is more traditional in the sense that you have basic blocks and you have conditional branches, and you have you have the CFG as well. So I also produce this graphical view in the dot format. People familiar with dot? So you can then visualize it and see how it looks like, what the flow is. So the idea was that once you have this structure, you can do optimization passes. At the moment, there's very minimal optimization implemented. So there's one which just throws away unused blocks. So when you're generating code, you can end up with blocks that are not needed, and so you just throw them away. So there's a very simple optimization. There's another optimization which I will show you in a second. But before that, wanted to talk about the fact that since the target is C, which we then compile, it's also possible, and I've been thinking about how to do this, to embed C code in Lua code. Because ultimately you're generating C, so you can merge the two together, right? And so I've been thinking about how to do that, and here's a quick overview of how it works. So you have, how do you embed C code? This is work in progress, this is still experimental, but you have some new keywords, C declaration. You can declare types, C types. There is some constraints that I impose. You cannot have pointers inside those types. I'll talk about why those constraints are there and what can be done about them. So you declare the type. You can then declare, so this is a Lua function. Sorry, I didn't mean to scroll past. This is a Lua function which is saying, okay, date functions is a table, and I'm creating a method called makeDate, which takes 3 arguments, date, month, and year. And I'm saying here, please allocate me a user data of this matching this type structure. So because the type has been defined, the size of the user data is automatically determined, and I'm saying give me one object of that type. So now in this field, date, I have got one object of this type which is defined here, and then I can have a chunk of C code which is, so there is a keyword called C unsafe. You can say what values from the Lua world you want to pass across to the C world. So here we have date, D, M, Y, they are being passed across into the C world. Then you have the C code where you can access those things. So if it's a user data type, you have to cast it to your required type yourself. Maybe this can be automated as part of the translation, but right now you have to cast you get a pointer to the user data object, but you have to cast it to the type you declared. You can then access everything in it. Any types that are here can also be written to, apart from strings. You cannot write to strings. You cannot pass tables here, and I will explain why these restrictions exist. And once if you write to any of these types, then they will be copied back, and that is what is used. For example, you can have methods which access the data object. So the data object is a user data, so once you get it, you can cast it and then access the elements inside it, and if you assign them to Lua variables, they will be copied back into the Lua world. So you can think of it like it's a way of data going into the C world and coming out of the C to Lua world within your Lua code without you having to write anything explicit, right? So why are the restrictions there? So there are some restrictions. So restriction is how to do it safely, that's the question. And so to do it safely, I decided that we need a full C parser embedded in the system, so we can completely parse the C code, analyze it, see what you're doing, and make sure you're not doing something you're not supposed to do. So there is a full C parser embedded in it. Currently I enforce certain rules, like you cannot make function calls to external code, but that's purely a restriction I'm imposing for safety reasons, but I have to figure out a way to allow that so that it's safe. And then pointers and structs are not allowed simply because of garbage collection issues, right? And that's why you can't access tables as well, Lua tables, because anything that's garbage collected, we have to figure out how to do that. So if you have a structure which has a pointer to another object and you allocate that in your C code, how are we going to deallocate it? What's the garbage collection going to be? So at the moment you can allocate C objects which are self-contained, don't have any references to any other objects, but you can allocate arrays of structures, but you can't allocate structures which contain pointers at the moment. I have some ideas about how to do it, but it's not there yet. Okay, and so the next thing the benefit of the new compiler framework was, can we do more optimization phases, like using standard compiler technology, like data flow analysis, etc., etc. I haven't done anything real with it yet because I'm still trying to sort out the basic stuff so that it's reliable, correct, works all the time. And I had so many bugs. Parsing Lua seems easy, but parsing part is easy, but the code gen part is not easy. There are a lot of subtleties, that will catch you out when you try to implement it yourself. So anyway, so here's an example of an experimental feature. A lot of times we want to declare constants, right? And if these constants are not changed anywhere, ideally they should be replaced by the constants in the code. So this kind of code where you I didn't show the code here actually. Okay, let me maybe scribble here. So what is the code supposed to look like here? Okay, so this code was something like you have local a equals 1, and then say you have a return function that returns a, right? So this was the function that I'm showing here. So it's a simple one. What you can see here is a is a constant because it's not being changed by this guy, right? So in the original version, without this optimization, we would return an up value because a is an up value as far as this function is concerned. If you're familiar with the internals of Lua, you will know about up values, right? So up values are variables in your parent function that you access. But we can analyze this and say, okay, look, a is not changing, a is a constant. So actually, I don't need the up value. And so you can have code in the new version when you enable this optimization, that up value has disappeared. And here you have just returned 1 because you know that the up value never changed and it didn't need to be an up value, right? Again, it's quite technical for people who don't know, I suppose. So my point is that the idea was the framework should allow you to do more optimizations, more standard compiler optimizations that today it's very difficult. And in terms of future directions, I'm just trying to, at the moment, stabilize a version with all the features I've built so far, so it's ready for, it's like production quality. So currently that's what my goal is. Obviously I'd like to add type inference, but it's a big problem because function return types are not annotated in this language at the moment. To annotate, I don't know, Roberto, if you can confirm this. In order to annotate function return types, you need nominal typing, right? You need to know when you require a module, you need to have a way to identify the function by the path of the module.function name, because you need to know the return type of the function. When you're importing a module, how do you know the return types of those functions? If it was just a table, you could not, right? Runtime, but not for a compiler which is ahead of time. So I guess in Perlin you must be using nominal typing. Yes, that's an alternative. Yes. But in the way that Perlin is doing it, it must be like when you require, you have nominal typing, right? Name based. So you know the module dot function is this type.
No, we use structure because it's exactly because remember that Perlin had the type in there is only what's called transient type. We do not ensure that the type is correct all the time.
Oh, I see. So when you require something, external module, how do you know the return type of a function? You can't.
You know the type as. You can know the type as it should know as it is declared, but it could be just array, or it doesn't need to be nominal. It could be structural, the same way as it should.
No, my question is more like you require an external module. Yes. That module is just giving you a table back of functions. So at compile time, you can't know what the types are, right?
If the other module is a Perlin module, it should be static. We have not implemented that yet, but
okay.
But probably you should be able to generate some kind of symbol file with the type representation of stuff in that module, and then we could verify as any standard Java compiler.
Yes, so you need to, in Java, you know, it's a nominal type. So you know from the module name and the function name what is the type of that, right? But in Lua, there's no such concept of a module name or a function name. So when you're importing, you just get back a table of functions. So how do you then?
What's the difference if you have structural typing? I mean, you should just get this is an array of records of.
Yeah, maybe we'll chat offline. Yes. Okay, no worries. All right, so sorry. And then And obviously there is an alternative way which is, suited for dynamic languages, is to detect types at runtime and then regenerate your code, right? And that's essentially what most JITs do. They basically have profiling information. They record the types, or at least that's what dynamic languages that try to compile dynamic languages do. So that's another option. So anyway, these are the things I hope to work on. In terms of challenges, it's a project I do in my spare time, so I have very little time to work on it. So things take a long time, unfortunately. And that's it. That's my presentation. Thank you. So yeah, if you have any questions.
So you mentioned for security reasons,
Yeah.
It's not allowed to use external functions from C code.
At the moment, I'm still trying to figure out how to do it.
I understand, but
because I would like to check the types.
Yeah.
When you're calling a C function, I want to make sure what you're sending to the C function agrees with the method or definition.
Yeah, I have a question regarding this. So hypothetically, if you manage to make it safe, so as soon as this feature is available, what would be the technique to specify which external library is used? For example, if you use, simple example, use printf.
Yes.
Yeah, so you need this standard C library to use it. So then you would have to tell the C compiler to use it. My question is, would you put this into C code, like some additional annotation, or where would this information be?
So the way I would do it is probably how LuaJIT does it. Is you have a declaration section in the C decal. Mm-hmm. You can also define the prototypes of the functions you want to import.
Okay.
And probably there'll be a way to say, I'm importing these functions with these prototypes from this shared library. So you will have this almost like a header in your Lua code. You have to have this because otherwise we cannot parse external header files simply because there's no standard format. Headers are full of operating system specific information. But if you could write all the C function prototypes, and if the language provided you with a way to say, I'm importing these from this shared library, then that's it. Then you would get a local variable, and then you just like LuaJIT does, you take the variable name and dot and the function name, and then you can use it.
Oh, cool.
But the important part is that it's still not safe, that particular approach, because as you know, shared libraries just publish the name. And the type you define in the prototype could be anything.
Well, regarding my approach regarding safeness would be compared to the safeness in C. There you also don't have it.
C is also not safe.
Yeah.
But if it was a C++ function, at least there would be name mangling, and so you would get the type safety.
So second question, did you ever measure the performance of your approach? Is this type information, for example, can you quantify it in benchmarks?
Yes, so I did that, and my experience, my own use of Ravi, is performance is overrated for a scripting language as a criteria. Many people start using, say, LuaJIT because they think, oh, it's going to give me some performance benefits, but they never sit back and analyze, did they really need that? Was it really something that... So if you're using Lua as a glue language, where you are using it to provide users a scripting ability, then I feel performance is not important, right? But if you're writing something like many people are doing, like you're writing your entire stack in Lua, like Kong does, like you guys do, then you need performance because you're writing an application in Lua, right? which personally I would never do, but that's what you guys do. Personally, I would always use strongly typed, statically typed language for large scale applications. So my use cases, I was using Ravi as a scripting language to glue things and to give users the ability to customize functionality, and which is what many people do. There, the native performance of your scripting language is immaterial. That's why Python is so popular, right? Because Python users are always using it as a script glue language. They're calling this external code.
Yes, that's true. It's a special case where you really need performance. And for example, in my case, which I presented, could be users that really want to do simple image processing in Lua. I really tried it, and it was fast.
Why would you do that?
Yeah, because to make simple experiments.
Oh,
so
okay.
there's a use case for this, although it's minor. Yeah. But I tried it, and Lua is really very fast. But this is my question. How much faster are algorithms when you introduce in Ravi this type systems?
So if it's numeric computing, you can get 10 to 20 times speed up.
Wow. Okay.
So it depends. You know, the benchmarks that we see, they're mostly numeric benchmarks, and that's where the performance gain is significant. Because if you imagine in Ravi, when you define an array, it's a C array, whereas in Lua, it's not. It's a table. Each object in the table is visited by the GC, for example, right? Because the GC doesn't know that it's a native array, and then you cannot access it sequentially in native code because each say you've got double array, right? In Ravi, when you declare a double array, it's just a C array, C or C++ array. But in Lua, everything is two. There are two. There's a type. You could say that it's like two objects, every element, right? There's a type object and there's the value object. So you cannot write C code to directly access that. So table access, if you were to access the same table in C code in Lua, you have to use the Lua API. The reason for that is it's not native C array. So, you know, performance gains for numeric computing can be significant.
Cool.
Otherwise, the performance for other things, like if you have a table, accessing a table, whether you do it from C or Lua, it's the same. It's a hash lookup. You're not going to gain anything. But if you were accessing an array of structures, and obviously your structure was, which you can't do in Ravi, you can't do that, but you can only do it through the embedded C option. So you could have an array of structures, and using the embedded C, you could work through that. That would be much quicker, right? So it depends.
Yeah. Okay. Thank you.
Anything else?
Maybe we can continue then with the next.
Okay. All right. Thank you.